we shouldn't go on further without stopping to investigate how the continuity equation came to be. We've talked about it, we've used it, but let's talk about where it comes from. It's a venerable principle of physics that shows up not just in this subject, but fluid mechanics, plasma physics, really a lot of different areas. And basically says what goes in must come out. And if it doesn't go in or come out, it must have been made inside or depleted inside. And that's what's depicted in this picture here. So I've shown a slab of semiconductor. So the semiconductor goes on in both directions. But we'll just look at a little slab with thickness delta X. These arrows depict current coming in, current going out, and loss and creation of carriers while we're inside of this. And carriers can be depleted or created. Those are two things that can happen to the carriers that go in. We can either add to them or we can take away from them. And so if we add to them, that's generation, and it can be done through a variety of processes. There's the impact ionization, which we mostly consider, which is a moving carrier hitting an atom and ionizing it, hitting a silicon atom and ionizing it. But there's photoionization, which we're going to be considering later in this chapter, where a photon strikes an atom and creates an electron-hole pair. There are also multi-particle processes like Auger, A-U-G-E-R, pronounced Auger, electron generation, and other multi-body processes. For loss, we just need to think about recombination. Electrons and holes find each other, and when they find each other, the electron goes back into the hole and you have nothing. It's an annihilation process where recombination happens. And so it's possible that a hole goes in and never comes out because it got captured by an electron. Let's label these arrows. The arrow pointing in is the current coming in. Instead of talking about amps, we can talk about current density J, which is amps per square meter, but then you multiply that by the area, and you have the amps. And if you divide that by Q, the fundamental charge unit, you have the number of carriers per second entering that slab. And we're going to talk about it in those terms. We're only going to talk about holes because if electrons are the exact same treatment, just swap out the P's and the N's. The arrow on the right is the current coming out. It looks the same expression-wise as the current going in, except for one little difference, and that is that the current comes out at a point that's shifted in space by delta x. So instead of J of x, it's J of x plus delta x. Otherwise, it looks the same. And then there's the generation and loss, generation recombination, input and outputs. And so that's what's happening. And we can put this in an equation. Let's start by putting this as a word equation. So what goes in must come out. So how are carriers added? Either by holes entering through the input current or by generation. And we've talked about the generation previously. We have this big G we've used, which is the number of electron hole pairs generated per second, per unit volume. So you multiply it by the volume, you just have the number of holes being generated per second. Don't worry about the electrons. That has to equal what comes out. So the current coming out and the recombination, which is loss. And we've talked about recombination before. So the excess hole density over the recombination time, tau. And you use excess hole density because you only have excess holes because you've created electron hole pairs. And so for every excess hole, there's an excess electron. So if you lose an excess hole, you've also lost an excess electron. We only worry about excess holes participating in recombination. That's the balance. What's added has to equal what's subtracted. Otherwise, you are accumulating charge inside this, or you are losing charge inside of this. And neither is allowed in continuity, in a consideration of continuity. Okay, so let's take that word equation, and let's go ahead and stick expressions in there. I wrote down the expressions for the rate that holes enter and exit, and we have these expressions for generation and recombination, so let's just put it down. For volume, we'll say area delta x. Area delta x. So there we go. We have a mathematical statement for the continuity. A little awkward. Current at J and current at J plus delta X. And I think I want to work on this a little bit to make it a more practical expression. Let's do a little rearrangement, and what I want you to do is pause this video for a minute and just convince yourself that you see how this third line happens. You know, the A's cancel and what else happens. Pause it. Do you recognize what's in the square brackets as the derivative? I hope so. I hope you recognize it as that. If you take the limit as delta x goes to 0, that's dj by dx. So we'll write it that way. Delta x only appears here in this denominator. Nobody's telling us what to use for delta x. Let's just take a really thin slab. Right? So then you replace that with the derivative. And you have this expression, which is technically, that's the continuity equation. The continuity equation tells you how the current density varies with position. And it's loss, the difference between loss and generation. I'd say loss minus generation is minus the current gradient. So that's it. That's the continuity equation. Except that we're going to put it in a different form. We're going to put it in a practical form for us that involves putting in an expression for the current density, because we've worked on that. Remember, there are two types of currents we've talked about, diffusion and drift. The expression for J for drift was just NEV or PEV for holes. And for diffusion, it has the gradient, the whole gradient in it, which could be convenient because, say, here's the whole gradient. Which one of those should we have? I mean, all you have to do is write them together, add them together. So this J could be the diffusion current plus the drift current. You can do that, and this will be the a more complete expression. I want to make our lives a little bit easier and make an argument. And the argument is this: the current is only due to diffusion. So we're going to ignore drift. But let's talk about why the current is only due to diffusion, because that could leave you wondering. Here, let's look at a p-n junction. P on the left and on the right. Remember, in a p-n junction, you develop a depletion region, which is where the space charge resides. So all the negative charge on the left and all the positive charge on the right, if you have the p-type and the n-type there and you bias it this way, forward bias it, it's a p-n junction. The voltage that you applied is V, and over here you have 0. Okay, so the voltage drop across this semiconductor is V. But all of the space charge is right here in the depletion region, which means the depletion region is your charged parallel plate capacitor. If that's the charged parallel plate capacitor, then all this voltage is dropped across the capacitive junction, the capacitive depletion region. And that means that there is no voltage drop across the neutral regions. And you can make that argument several ways. You can make that argument with Gauss's law. You can make that argument the way I just did. But there's no voltage drop across the neutral regions. And the bulk of a semiconductor is neutral. And so if there's no voltage drop across a neutral semiconductor, there's no electric field inside. And if there's no electric field inside, then there's no drift current, because drift current is proportional to electric field. So you can argue that any current we see is from diffusion. Having discussed that, let's go back to the expression, the continuity equation, and put in the current density that we want to use, the diffusion current density. And we've gone through that, right? The whole diffusion current density is minus QD, the whole diffusion constant, times the gradient of whole carrier concentration. Now we have something that we can use. Okay, run that second derivative through. Q and D, big D are constants. So I have this question. What about P? Okay, there's a P prime, the excess hole concentration, and this is P, the hole concentration. What should we use? What do we do about that? Well, it's actually a very simple matter. The hole density throughout a semiconductor is the equilibrium hole density, P0, plus the excess hole density, P prime. Well, P0 comes from the doping. So if the semiconductor is uniformly doped, this gets simpler. And so we'll assume uniform doping, right? The total hole density is the equilibrium hole density, P0, which is n sub I squared divided by n, plus the excess hole density. And only the excess hole density has position dependence. in this derivative, p can be replaced with p prime. So go ahead and do that. You just write p prime instead of p. And you have this final expression. I factored out the big D and the Q. You can call that the continuity equation. That's what we're going to use. And there's an equivalent one just for electrons. Replace the p's with n's. That's our continuity equation. It ensures physical nonsense doesn't get realized because what goes in will be what comes out. And so we're going to use that, and we're going to use that quite a bit now in the rest of this chapter. So stop at that.